Hello students, it's Nazia Begum here, your physics lecturer, welcoming you all in today's lecture. So today we are going to further discuss about molar specific heat of gases. So in previous lecture we have discussed what is specific heat. So once again I want to revise that. Specific heat is that amount of heat which is supplied to a material of a unit mass, an object of unit mass, to raise its temperature by uh, unit degree. Okay, so if suppose we are having 1 gram of object and we have to raise its temperature by 1 degree centigrade, so to raise that much temperature, how much amount of heat is required, that is called specific heat. Okay, and specific heat is different for different materials. It depends on the nature of material, as well as it also depends on volume and pressure. Okay, so depending upon whether the volume or pressure is kept constant during heating of a gas, the molar specific heat of a gas is of two types. Okay, so whenever we have to raise the temperature of the gas, so at that time uh, two ways are there. Either we can make the pressure constant, or we can make the volume constant. Okay, and by keeping any one physical quantity constant, we supply heat to the gas. Okay, and in that case whatever heat is required is called the specific heat at that particular constant quantity. Like, specific heat of two type, heats are of two type. First is molar specific heat at constant volume. So if suppose 1 mole of gas we are having and we are supplying it heat energy by keeping the volume constant, so it is called molar specific heat at constant volume. Second is molar specific heat at constant pressure. So if we are having 1 mole of gas and we want to raise its temperature by 1 degree, so if we keep the pressure constant, okay, by keeping the pressure constant, if we supply heat to the gas, so that time whatever specific heat will be there, that is called molar specific heat at constant pressure. Okay, so now let's discuss each type of molar specific heat separately. So first is CV, that is molar specific heat at constant volume. So now you imagine that we are having a container. Okay, we are having a container, okay, in which a piston is there, and this piston is fixed at its place. That means it cannot move. And inside the cylinder here gas is filled. Okay, now whatever amount of heat we supplied to this gas, that whole heat will be used up in raising the temperature of gas. Actually here the volume of the container is fixed. Okay, so whatever energy we are giving to gas, the particles of the gases, the particles present in the gas, they absorb the heat and they get their kinetic energy and they start moving in random directions. Okay, in their way of moving in random direction, they collide with each other and with the wall of the container. Okay, and because of the collision, the temperature inside that container increases. So the temperature of the gas increases. So whatever energy we are supplying here, all of that energy will be used up in the increment of the temperature of the gas. Okay, so when the volume is fixed, so whole energy, whatever heat energy we are supplying to the container, is used up to increase the temperature of the gas. Okay, so keep this in your mind. Now let's discuss CP. Okay, now suppose we are having a container. Wait. we are having a container in which a piston is fixed. Okay, this is the piston, and this piston, sorry, I said fixed. This is the piston which is attached to this cylinder, okay, this container, and it is movable piston. It can move. That means the volume can change. Okay, so now suppose inside this piston gas is filled there, and when we are supplying heat to the gas, okay, so the particle of the gases, they are absorbing that heat energy and they are converting that heat energy into kinetic energy, okay, and they start moving in random direction. They start expanding, okay, they go away from each other. So in that case, what happened, when they start moving in random direction, they start colliding with each other and the pressure there start increasing. But here in CP, we have to keep the pressure constant, okay. So to maintain the pressure inside the container, what we will do, we will move the piston, okay, whatever heat energy we are giving to the particle, okay, so that energy is completely not used in raising the temperature of the particle, but some amount of the energy will be used here to increase the volume of the cylinder, okay. And why we have to increase the volume? So that the pressure will be maintained. If the volume is fixed, the pressure cannot be maintained, okay. To keep the pressure constant, we have to increase the volume of the piston cylinder, okay. So by moving the piston in upward direction, okay, if we move the piston in upward direction, so the volume of the container will increase, hence the pressure will decrease and it will become in initial status, okay. So here the pressure will become constant. But here then what happened? Because the volume has increased, so the chances of collision between the particle decreases and hence the temperature will not increase so much. Okay. In case of constant volume, what was happening there? Because the volume was constant, that's why the gases has to be there in a particular, in a certain volume. Within that volume only they have to move, and that's why the chances of collision were more there. But in this case of constant pressure, because the volume is increasing, that's why the chances of collision between the particles decreases, and that's why the rise in temperature also decreases. So here when uh, there is constant pressure, the increase in temperature is very slow. So that's why here more amount of heat is required to raise its temperature. Are you understanding this? In case of CV, less heat is required to raise the temperature of gas because the volume was fixed. That's why the temperature was increasing fast. But here in case of CP, because the volume is not fixed, that's why we need more amount of heat energy in comparison with CV. Okay. So if more amount of energy is required in case of CP, so we can say that CP is greater than CV. Is it clear? Because Cp is the amount of heat energy which is required to raise the temperature of a gas at constant pressure, and Cv is the amount of heat energy which is required to raise the temperature of a gas at constant volume. And from the discussion which we have done right now, we understood that in case of constant pressure, we need more heat to raise the temperature. That means Cp is greater than Cv. Okay. Now let's see the definition of Cv. The molar specific heat of a gas at constant volume is defined as the amount of heat required to raise the temperature of 1 mole of a gas by 1 degree when its volume is kept constant. Then Cp, it is defined as the amount of heat required to raise the temperature of 1 mole of a gas by 1 degree when its pressure is kept constant. Okay. Then whatever is given in this paragraph, this thing we have already discussed. Okay, that at constant volume and at constant temperature, in which case we need more heat energy. So one thing is clear there, that Cp is greater than Cv, or we can say Cp equals to Cp plus W. Okay, why here we have written Cp plus W? Sorry, Cp not, it should be Cv. Cp equals to Cv plus W. Okay, because here what happened, in case of Cv, whatever amount of heat energy we are giving to the gas, whole energy were used up in raising the temperature. But in case of Cp, with rise in temperature, the heat energy was being used by the container, the gases, for one more thing, and that was the work done on piston. Okay, if we are increasing the volume, so we have to do some work on piston. So gases there, we are doing some work on piston. Okay, so that much amount of heat is extra there in case of Cp. So that's why Cp equals to Cv plus W. Now let's move to next topic, that is calorimetry. It is the branch of physics that deals with the measurement of heat transferred from one body to another, and hence enables us to determine the specific heat or latent heat of a substance. Okay, it works on the fact that when two bodies at different temperatures are placed in contact, the heat lost by the hot body is equal to the heat gained by the cold body, provided there is exchange of heat with the surroundings. Okay, so heat lost equals to heat gained. This is also called as the law of mixture. Okay, so in calorimetry, we use a calorimeter which consists of a cylindrical copper vessel. Okay, so here in front of you, you can see this is one cylindrical copper vessel. Inside this vessel, we will fill the warm water. Okay, and actually this was in your practical last year, but this time we are not doing practicals, we are not doing experiments. So if so, it is a little bit complicated to understand, but if we were doing the experiment, so it is a very interesting experiment. And let's see. So here is one copper vessel. Inside this vessel we will fill the warm water. Okay, now we put this copper vessel inside a glass container. Okay, which is a non-conducting material, it does not conduct heat. Okay, and inside this glass, what we say, sorry, glass not, inside this wooden box, we are having wool also here. Okay, here it is completely filled with wool. Why wool we fill? Because wool is also a non-conducting material. So whatever heat is there, okay, in copper vessel, the water is filled there, so whatever heat that water is having, that heat is not transferred in these directions. Okay, sidewise transfer is not there. Why? Because non-conducting materials are filled there. So whatever heat will come out from this from the water which is filled in copper vessel, that heat will come out from this upward part only. Okay, and this part is also covered up with a wooden lid. Okay, one thermometer we put inside the water, and we note the time interval, that in a particular time how much degree of temperature decreases. Okay, and in between noticing the temperature, we are stirring the water with the help of the stirrer. Here we are having one stirrer. Okay, with the help of stirrer we are stirring the water. And why we are stirring the water? Because water is a fluid, and fluid is having the tendency that when it becomes warm, it raises up. So what happened when the water start losing its heat? So its temperature will decrease. So whatever water whose temperature will decrease will go down, okay, and whatever water particles or water molecules whose temperature is more will come up, okay. So here in upward part all the hot molecules will accumulate together, and in the lower part all the molecules which are having uh, means less heat, they will accumulate here. So the thermometer will not give us the correct reading, but when we stir the water, so that time hot water and cold water they all get mixed up, and that time the thermometer will show us the correct temperature of the water, okay. And when we are doing this experiment and noticing the time that in one particular time interval how much temperature is decreasing, that how much temperature is being lost by the water, so we come to a very good conclusion. What we notice here that initially the temperature decreases very fast, but after some time when the temperature difference between the water and the surrounding becomes less, the decrease in temperature also become very slow, okay. So here after doing this experiment we also come to one law, we also come to know about one law which is called Newton's law of cooling, okay. So here you can see Newton's law of cooling is written there. So according to Newton's law of cooling, first we will read its statement. It states that the rate of cooling of a body is directly proportional to the temperature difference between the body and its surroundings, provided the temperature difference is small, okay. Temperature difference should be less than 40 degree, then only this law will be applicable. So to explain this law in more easy manner, I want to give you one example. So whenever you are drinking tea or warm water, so if you simply leave them like that, okay, suppose you are having a cup of hot tea, okay. So if you simply put the cup on table or somewhere, so you feel that initially the tea is very hot, but after some time it becomes lukewarm, okay. Very fast it becomes lukewarm, but from lukewarm to come in a normal temperature it takes a very long time. Why does it happen? Because initially the temperature of tea was very high, and in comparison with surrounding, if we find out the temperature difference, so the temperature difference is very high, and according to Newton's law of cooling, the rate of cooling of a body is directly proportional to the temperature difference between the body and its surrounding. So if the body is very hot, okay, and temperature difference between the body and surrounding is very high, so that time the body loses its temperature very fast. But when once body started losing the temperature, then slowly the temperature difference between the body and surrounding started decreasing, okay. Now suppose I am just giving you an example that the room temperature is 23 degree, okay, and we are having a cup of water whose temperature is suppose 60 degree. So 23 and 60, what is the difference here? Here the difference is of 37 degree, okay. So here the water will lose its energy very fast. Now suppose the water has lost 4-5 degree. Now the temperature of water becomes 55 degree, and what is room temperature? It is 23. So now what is the difference? Now the difference between the water and surrounding is 32 degree. initially it was more than that. Okay, so slowly what happened, the temperature difference decreases as the body started becoming cooling down, so the temperature difference also decreases, and hence the rate of cooling also decreases. And this thing we can experience in our day to day life as well. If any body is very very hot, and when we keep it in a room or in any place, okay, so in starting the body loses its temperature very fast, okay, and from very hot it becomes less hot very fast. But if the body becomes lukewarm, okay, so from that lukewarm condition to come in the normal condition, to come in the normal temperature, the body takes a very long time. Okay, so this thing is practically means we can see everywhere around us. So today we have discussed about specific heat at constant volume and pressure, and also we had some idea about calorimetry and Newton's law of cooling. Now in tomorrow's lecture I will explain the derivation of Newton's law of cooling. Okay, till then, goodbye, take care, do some productive work, and the most important thing, be healthy, be safe.